So I'm going to present a work that I made in collaboration with Andrea and Daniele a couple of years ago, but I think it's still relevant. So I wanted to start with a disclaimer that this is an our perspective, so feel free to say your own opinion. I'm really curious about your comments later. And that's kind of also a common practice in OR, so I hope you won't find it too boring if you already are into this kind of mindset and framework. So I think that we are in a very exciting time in machine learning because recent advances in the techniques, but also increasingly powerful hardware. And you can see that there are so many papers and works that are published monthly and daily and so on. Not only about VRPs, but combinatorial optimization problems in general and many other, optimization problems, as we have seen also this morning. What I think it's kind of the recurring them in all of these approaches is that what's happening is that they are trying to somehow support the design of the algorithm by decreasing the manual engineering that's required. And that's a quite cool I think, quite cool thing that's happening. So just want to give you some numbers. I'm sorry, it's not well formatted, but if you search on Google Scholar for these two keywords, vehicle routing and machine learning, as you can see over the years, there's been this growth here in the numbers of drafts and papers that are published, at least collected in Google Scholar. So I think it's a quite relevant topic. As for the motivation of this work, so basically what we have found is that sometimes it's of course not always the case. There is some, the computational testing of these approaches is a little bit different from what we are used in OR. And that's a little bit risky because the risk here is that very promising approach are a little bit overlooked because just because of the computational testing which is done differently and may not be that appealing from our perspective. So our goal was that of trying to define, a common testing setup for both approaches, which is what we say, which is the OR one. So we're trying to impose it basically. So as for the scope of this presentation and the work, so it's about traditional VRPs, so not fancy stuff like dynamic problems, stochastic, and so on, but just traditional ones. I'm going to give you some suggestions, which are, most of them are quite general, but there are some few specific for machine learning approaches. But if you really want to become a real expert on doing computational studies, I really strongly recommend reading and studying this beautiful paper here. So let's jump into the first section. By starting from the very beginning, so the problem definition. So we know that VRP identifies a very broad family of problems, and each of this problem has its own very precise and definition and formulation. And on top of that, we may have that there are some dataset specific conventions, right? And here you have some examples, but I want to talk about I think that happened to me personally. So I was working on a VRP. And the customer demand was defined to be a floating point. And of course, you find a paper where this was solved as an integer. You find a paper where it's solved as a floating point, single precision instead of double precision. And of course, that doesn't work. I mean, we cannot really have comparable results if we are solving different problems. So I know that's the first obvious suggestion, but in order to have comparable results, we really need to solve the same problem. Now, once we pick a problem, we typically want to solve some instances. And as far as I know, even though I'm not an expert here, if we are using some supervised machine learning model, we typically need a lot of instances that are sharing the same characteristics. What I've seen sometimes is that these are randomly generated, they are solved, and then some conclusion, some, comments is done on these results, right? So I would say that this is far from ideal because we know that VRPs are NPR from a theoretical point of view, but I think that the actual challenge that an instance really poses is defined by some factors, which are here. You can see some of them here, and for this reason, so the community which is expert on that specific problem typically identified a set of instances which can be considered to be relevant for modern approaches. So our suggestion is basically to just include also these well-studied literary instances in the comparison. I mean, that's another obvious suggestion, but sometimes it's not followed at all. there may be some reason, because I mean, there may not be enough instances for the training and the validation, and unfortunately that's true sometimes. Luckily, I think that things are slowly improving. Now, for example, for the CVRP, we have some instance generators, and here you have one. The formatting, but yeah, just wanted to, let's say, ask whoever introduced new instances, please, if you're introducing instances which are not based on like real-world data, I mean, consider like providing these instance generators to the community. It's a very nice contribution. The second point, I think the third one won't fit into the slides, but yeah, is to, we can definitely try to emulate the instance generation process to generate new instances based on certain distributions. It's a little bit trickier because so it's more error prone, definitely, and sometimes some details are not in the paper, so it's just different. So if the first point is available, I would strongly recommend using generators. And finally, as a last resort, I would try to reach out to authors because maybe they have the scripts, but they've just forgot to share them with the community, right? Once we have generated the instances, we should use them for the training phase, and of course using the public available ones for the validation of the method. Here you have some popular repositories, but I'm pretty sure you already know about them. So we have VRPrep, which includes a lot of different problems, but I'm not sure whether it's still well maintained or, yeah. CVRPlib is definitely super well maintained, but till right now it's just for CVRP and VRPTW, but maybe in future, who knows. And then we have the classic ones, but I think they have not been maintained since, I don't know how many years. So the second point is about the selection of baseline and competitor algorithms. I think that we can agree that the evaluation of algorithms could be done along these 4 dimensions. So the effectiveness, so how capable an algorithm is finding good quality solutions, efficiency and scalability, so how fast the good quality solutions can be found, and like what sizes can be safely, let's say, without crashing the laptop, be supported. The generality and flexibility, so how many variants are supported and how difficult it is to extend. And finally, the complexity, so how many components and whether they're well justified and how much manual engineering is required. So I think that data-driven approaches are quite good at lowering the complexity requirements because, you know, they are learning some stuff from data. So we don't have to do the design for that part, at least like as I understood it. And in fact, if you check these papers introducing new methods or using these data-driven techniques, they typically don't solve a single problem, let's say a single VRP problem, but they typically solve several, even, let's say, unrelated, not only VRPs, but, you know, you can find papers solving several combinatorial optimization problems using the same technique. However, I still think that evaluations should definitely include all the other dimensions as well. Because what I found is that sometimes, at least this happening for, say, these traditional problems, the papers only consider simple baseline and other competing machine learning approaches. And maybe, so because they are not, let's say, state-of-the-art on the first 2 dimensions, which, by the way, are the simplest one that we can quantify. So I see why some papers are really focusing on them, unfortunately. I would say that shouldn't be really a problem because I see that the goal of these approaches is not necessarily that of outperforming like state of the art, but that of being quite versatile tools, right? However, I still think that it's like very important to have an objective evaluation of the first 2 dimensions as well, because otherwise we are really like distorting the results. So another obvious suggestion is like to try to always include the best available state-of-the-art algorithm into the comparison, because this will also help us understanding like the trade-off between data-driven and crafted approaches, right? So typically, the selection of algorithms is guided by the availability of algorithms. And luckily, as we have seen, like also this morning and now, more and more researchers are sharing their solvers. I just want to raise let's say a word of caution here. We should not misuse these solvers like by just taking them and using them out of their context. Like solving instances for which they were not designed and tuned. because then the comparison won't be fair at all. And here I want to ask you whether we should have, as we have for the instances, like a website or some references where we can like find open source algorithms, the instances that they are solving, like all in one page. That could be like very cool, I think. A few words about programming languages. So sometimes we have to implement these baselines. This typically happens for very simple, like constructive algorithms. I would still like really use appropriate programming languages and data structures. So I don't know whether it's me, but I would never implement a for loop in Python and then don't feel bad about it, but maybe it's me. So yeah. A few words about XSAT solvers. So I've seen them into a set of baselines as well. I would definitely not do that because it's like comparing apples and pears, because the goal is that of proving optimality and not finding good quality solutions in reasonable computing time, at least. But if you need to generate training data, then yes, they are quite nice for medium, say small to medium instances. And but I wouldn't use an XSAT, say general purpose solver. But we have just had this presentation about VRP solver and the nice Python interface. So that is, I guess, more effective and to be preferred over an XSAT solver for VRPs at least. Finally, last section is about algorithm comparison. So I think that in general, comparing algorithms is quite a difficult task, but in this case, it's even more difficult because like these two let's say approaches have different nature. So on the one side, we have that typically these traditional approaches are designed to be, on average, let's say, quite good over a set of instances that have a very broad set of characteristics, which can be also coming from different data sets. And typically what happens is that there is a single design, a single tuning, and then we have the results for all the instances. On the other side, sometimes let's say a tuning is required for every instance distribution. So you see that already it's quite difficult to have a, say, fair comparison. From a more, let's say, practical point of view, we have that these traditional approaches are typically implemented in highly performant languages. I think about C, C++, Rust, and Java sometimes. And they are typically executed in this, say, environment, which is CPU single thread. And I'm coming back to that later. While these data-driven approaches are implemented in mixed languages, like interpreted language plus some native libraries, and they are sometimes they are executed by using some CPU and a little bit of GPUs as well. I think that there are two, let's say, environments where we can execute algorithms. There is a production environment where like it's when we are like solving a problem for a customer, right? And there I understand that we should use the best available resources and technologies. And of course we can parallelize say XSAT solvers, we can parallelize easily population-based algorithms. I've also seen weird stuff with computing QPaths or NGPaths on GPUs with incredible speed ups. But that was the parallel computing paper. And then we have the experimental environment, which is the environment where I think we are when we are comparing, say, algorithms between us, among us, right? This, I think, it's a more like artificial environment, and here we really want to like minimize like the noise, which would make like the comparison more challenging without really adding a lot of value to it. So our first, say, obvious suggestion is that of try to run all solvers by using a common configuration. This means, yeah, it's fine to like run it on specialized hardware, but if possible, I don't know whether it's always possible, I would try to run it also on commonly available hardware, and I think that the simplest possible setting would be what we are currently doing in OR, so a single thread and standard CPU architectures. What I've seen in some papers is that they were able to come up with this rough evaluation of the GPU speed in terms of number of CPU cores. I think that's still quite valuable and interesting information. I don't know how they did it, however. That's tightly linked with the previous suggestion. Because if we want to run all solvers by using a common configuration, we need to get access to the solvers. So I understand that's not always the case. We don't always want to give our work for free, but I would sometimes, if you feel it's a good idea, consider open sourcing the implementation. It's a great contribution to the whole community. And we have, as we have just seen today, a lot of things, nice things could happen on top of these solvers that have been released. One can also just consider sharing executable, maybe with hard-coded instances, so that one is sure that it won't be misused, let's say. And this, I think, it's a quality of life improvement that we all should do, like share computational details in easily accessible formats. I don't really want to copy-paste from PDFs hundreds of tables and numbers by doing having these weird characters pasted, right? So I'm really sorry about the format, but it worked well on my computer. So sometimes we cannot just run again a computational study because maybe the implementation is not available or it's too time consuming. So what's the common practice is that of scaling the computing time by using some appropriate factors. And we have started using this Passmark software to get these factors. So I understand that relying on third-party services, it's not that great because they may become they can ask money for that at some point, or they can be just shut down at some point. But that's the current, let's say, practice. I know there were the Dongar equation resolution, but I'm not sure whether they are still a thing. However, I think that they are doing quite similar stuff with some additional tests to get the statistics. By the way, on this website, one can look up its own CPU and then access the single thread rating so that it can be used to scale the computing time. But we know about it. I mean, we used it for the DIMACS challenge. The nice thing is that we can submit new samples. So if the CPU is not there, one can run their own tests on the laptop or workstation, whatever, and can submit the samples. But this also means that the score changes over time. So make sure to include the complete CPU with all the details so that it can be looked up in future. Okay, that's another obvious one. But for randomized algorithms, definitely we should compare averages and not best or whatever. Because even if it won't be a very significant, let's say, in terms of statistical analysis, it would be just a better indication of the algorithm performance. Okay, I'm missing here. There was an emoji, but by the way. Also report the computing time. So the complete computing time, I've seen papers just reporting, but that's not really related to machine learning related stuff, but also in traditional papers, let's say. Only computing the time to find the best solution, that's definitely not ideal because then no one knows whether, maybe I can put myself here. No one knows whether more time would really allow for an improvement in the solution or not. Consider the inclusion of charts, which are, I think, quite nice in papers and quite effective for a visual comparison. For example, here we have 3 examples, but performance chart, which shows dominated and non-dominated algorithms, speed of convergence, and the variability, like box plots. We have seen some today as well. So unfortunately, these only measure the first 2 dimensions, like effectiveness and efficiency. I don't have good suggestion for the other ones, but maybe you have some. And finally, I want to say a few words about statistical relevance. In the past, I think that comparing the averages was kind of okay. But nowadays, since algorithms are getting better and better, the difference between their results is narrowing. So it's sometimes very difficult to just say one algorithm is better than another one just looking at the averages, right? So what I've seen a lot is the inclusion of simple statistical tests to help in this regard. Maybe they have their own limitations. I'm not a statistician, so but since I think they are kind of quite nice addition to our toolset, and they are also used in a lot of other fields. So my girlfriend is a biologist. She's using these tests a lot, and so I think they have some value. So here you have an example. So what I've seen a lot in papers is this Wilcoxon signed rank test. which is nice because it allows to compare like paired observations, so basically pairs of algorithms, and doesn't require any assumption that there's a distribution. So as an example here, you have two algorithms, and it looks like that the first one has a lower gap, so it's better, right? So what we can do, we can define a null hypothesis, which basically says that the two algorithms are not significantly different in their results. An alternative hypothesis, which says that the first algorithm is worse than the second one. And by picking a significance level, which gives us the confidence of the test result, we can evaluate the hypothesis, right? And here are a few numbers. I've not made them up, but they are real. So if you compute the p-value, and you compare it with the significance level, which I've seen used a lot in papers, we cannot really reject the null hypothesis. So despite like the average result, the average gap of the first algorithm being like lower, considerably lower with respect to the second one, so we can't really say that the results are statistically different. And by the way, this test can be like really done with a few lines of Python or R. So finally, and this is my last slide. So I think that that's always a thing which is nice to find in papers. So what happens if some components is tuned differently or completely disabled, or when a complex component is like replaced with a simpler one? I think we have an example here from a recent paper from Thibaut and Andrea and co-authors that find that shows how, like, if I'm not wrong, like a crossover made with some neural network can really be made with a simpler alternative without really lowering the results. Okay, and that's it from my side. I made it faster than I expected, so there's plenty of time for questions. And yeah, okay, thank you.
Can you say something about reproducibility?
Yes. What do you want me to say? So, yes. So, yeah, I think it's a very important aspect of the work. I mean, also linked with the previous, let's say here, suggestion. We definitely should somehow make other researcher, let's say, be in the position of really checking whether our results are, let's say, what are in the papers or not.
In the last few years, industry uses the cloud or the sky to compute. Can you say something about that?
About clouds?
Clouds and sky, the sky, yeah.
I see what you mean.
How do you compare?
Okay, so you are basically asking whether, like, doing computation on our own workstation or whether using the
In practice, that's what they do these days.
Yeah, so I think that the risk is that not being able to, like, to do the same experiments by making sure that we are using the same machines, because I think that they are changing them quite often, or I have no idea. I've never used actually cloud computing. Yeah.
Okay, just a question remark. I think that the best way to achieve those goals, the journals should require some kind of this, like this, that you can do reproducibility. Because otherwise it's improving, but too slowly. I think the journals should start requiring that the papers should be together with the code, with the instances, with everything. So even if the code is not open source, at least the executables should be available. Mm-hmm. So I think that there should be a discussion between the editors and the area to really require this, like mathematical program computation. Does that for 13 years. Because otherwise I see this progress will be very slow.
Actually, I think that the machine learning community is far more progressive in this regard. I mean, you always find the source code, or most of the time, linked to papers. While yes, in our field, yes, it's not that. I mean, it's improving, but not slowly. Yeah. Sure.
Just another comment also. I think the machine learning community is more prone to share code because they are computer scientists. They know how to code things properly and stuff. Our discipline is more heterogeneous. You have people from business schools, engineering schools, and mathematics that are not necessarily the best coders in the world. And some people might feel too ashamed to share their code. That's my personal feeling. I don't know if I'm right.
I see your point.
And I would add a bullet.
There is a lot of spaghetti code in computer science.
As well,
Yeah. But they are less ashamed of it. And just, I would add a bullet to this slide. I think something that we don't do enough is to share solution evaluators.
Okay.
Like when you propose a new set of instance or for a new problem, if you just publish some piece of software that evaluates the solution in whatever format you decide, I think it helps a lot of reproducibility. I mean, in the old variants of vehicle routing, it's not too difficult. You just compute the distance matrix and that's it. But for anybody who has worked in some kind of a stochastic variant or electric VRPs where the approximation of the charging function can be here, how you interpret it or not, it's just too difficult to compare to other people because you never know if you're comparing apples and apples or not. Okay. So I think this is a thing we don't do enough, and I think that will help in reproducibility.
Also, certificates of optimality.
Yeah.
How do you know they computed the optimal solution?
Yeah. I mean, this was about heuristics, but I see. Yeah. Definitely yes.
Questions? So, thank you, Luca.
Thank you.